Okay, so if it exists, the steady state distribution satisfies pi times q equals 0. This is the global balance equations. And again, similar to what we had done with discrete time Markov chains, we define the limiting case of state transition probability matrix, PT, and we denote with P to the infinity. And of course, if it exists, if this limit exists, and remembering that the derivative of P of t equals P of t times Q, as we have derived earlier, in steady state, if this limit exists, this derivative will go to 0, okay? Therefore, and this will at the limit go to P infinity. That means P infinity times Q will be equal to 0. So here we have a very similar case with similar to discrete time Markov chains. And over there we had the P to the power n was converging. All rows were left eigenvectors of matrix P. But here we have P infinity matrix converging. Okay, if the limit exists, um, every row of the P infinity matrix, the limiting case of PT, will be a left eigenvector of Q corresponding to the eigenvalue of 0. Okay, so that's another way to compute the steady state distribution if it exists. So one way to compute the steady state distribution is solving this along with the sum of pi i's being equal to 1, of course. Or rather, maybe you can check for this, P infinity. But also remember that pt is equal to e to the power qt. So this p infinity, by definition, should be equal to the limit as t goes to infinity, e to the power q times t. So what you can do is, if you have a computer, for instance, you can compute for large t values e to the power q times t and see whether all rows converge to the same vector. In which case, you can say that that row is the steady state distribution. So again, here we have a number of ways to compute the steady state distribution. Either you can solve global balance equations, or you can compute the left eigenvector corresponding to the eigenvalue 0, or you can compute e to the power q times t for large values of t and see whether all rows converge to the same vector. Let's see this on an example. Well, if you recall the two-state Markov chain from earlier, we have state transition rate from 1 to 2 as lambda, and state transition rate from 2 to 1 as mu. And this is our infinitesimal generator matrix. And we had found earlier the state transition probability matrix with respect to time. Okay, this was the solution. Now, if you have a close look here, we have components of the form lambda or mu times e to the power minus lambda plus mu times t. Okay, obviously lambda and mu are rates, so those are positive. Therefore, e to the power minus lambda plus mu times t, as t goes to infinity, is going to decay to 0. So these terms, this one, this one, this, and this, are going to die out as t grows. Okay, so what we will have is mu divided by lambda plus mu, and then lambda divided by lambda plus mu. And in the second row, again, mu divided by lambda plus mu, and lambda divided by lambda plus mu. As you see, both rows converge to the same value. Therefore, this will be the steady state distribution. Mu divided by lambda plus mu, lambda divided by lambda plus mu. They add up to 1. And obviously, you could also have obtained this from pi 1, pi 2, multiplied by q, minus lambda lambda, mu minus mu equals 0, 0. Okay, if you expand this expression, well, of course, you will obtain two equations, but one is going to be equivalent to the other. So replace that by pi1 plus pi2 equals 1 and solve. This will give you the same result. Or alternatively, you can plug this in pi and see that this, in fact, evaluates to 0.